What's up, guys? We are still working here in Chapter 6. We're going to be working on some problems that are related to what we're doing in Chapter 6, but you don't find them necessarily directly out of Chapter 6. But they're things that you definitely need to be aware of. So you want to write this down. Mixture problems are when you're mixing two solutions to make a new solution. We'll be looking at those in just a second. And distant problems involve two things traveling a particular distance. In other words, two trains leave a station. Just so you know, this is more of the focus. I'm going to treat both of these more like distance problems. These are not the only way to solve these kind of problems. It's just the particular way that I'm going to be showing you. So distance problems really is our basis of everything. So before we jump into this, I just need you to remember that distance equals rate times time. Everything that we're focusing on today is based upon this equation. All right, so make sure that you have that copied down. Before, otters, they are funny little creatures, and they're pun masters. Here's their pun. I think you've confused me with someone who builds a dam. Otters don't build dams, people. Beavers do. All right, mixture problem says a nursery sells Kentucky bluegrass seed for $5.75 per pound and tall fescue seed for $4.50 per pound. The nursery sells a 5-pound bag of mixture of the two kinds of seed for $5.25 per pound. How much of each kind of seed does the nursery use in mixture? So you're probably looking at this and thinking, what the heck did I just read? Understandably so. They're confusing. So in order to help with this confusion, one of the things that I want you to do is to make a table. And we're going to have a couple headings here. So first of all, we're going to have, I'm going to call it rate and time and distance, because rate times time equals distance. Even though this isn't a rate problem, I'll show you what I'm talking about here in just a second. So this is kind of our basis for this. So we're going to make this table. And if it's a mixture problem, there's going to be 3 different rows here. Okay, so for our first one, we're going to have our first grass seed, which is going to be a Kentucky bluegrass. I'm just going to call that KBG. And then for the second one is tall fescue. And then this third one is the mixture. Okay, I need to write these things out. Now I'm going to just start filling in values on this table. Now I'm going to tell you right now, usually you don't know the distance. Okay, and this will make sense in a second. But a rate is something that's always per. Okay, so to fill in the rate stuff, I'm going to find all the pers that are in here. So Kentucky bluegrass is $5.75 per pound, so I'm going to call that my rate. Which a rate, that is a rate. That makes sense for that one. Tall fescue is $4.50 per pound, so I'm going to put that right here, 4.5. The nursery sells a 5-pound bag of the mixture. Now, this is the amount where it's like a rate is normally multiplied by a time to find a distance, but we're not multiplying by time. We're actually multiplying by an amount. Okay, so I'm going to fill this in, and we're going to say that this right here is going to be the money. This right here is going to be the pounds. Okay, in a normal rate problem, you'd say the speed times the time equals the distance. In this one, the cost times the amount per pound. Okay, or the number of pounds times the cost is going to equal the total cost. And that's what we're writing out here. So the distance in this case is our cost. Okay, so it says the nursery sells a 5-pound bag of the mixture of the two kinds of seed for $5.25. How much does each use in the mixture? So the mixture is 5 pounds. Okay, so we got some other things that we need to fill in here. It says how much of each kind does the seed use? We know that the mix is $5.25 per pound. So you would say, well, that's the cost of this, that's the cost of this. I need to find the one that's in the middle. The Kentucky bluegrass, I don't know how much that is per pound, so I'm just going to call that K. Now, if I use K, Kentucky bluegrass, an amount per pounds, then I know that this has to be 5 minus K. Because the mixture is some of this plus some of this is 5. So if I call this one K, I'm going to call this 5 minus K. It doesn't matter which one it is. I could have done tall fescue down here, but that's the one that I'm going to go with right here. All right, so from here, my distance is always going to be this times this times this times this. So I'm going to have 5.75 times K. That gives me the cost of the Kentucky bluegrass. The cost of the fescue that's included in there is going to be 450 times 5 minus K. And then the total mixture itself is going to be 5 times the price per pound. And right there I filled out my table. Okay, so this is a big part of this problem right here, is filling out this table. The next thing is I need to write an equation that's going to represent this problem. Okay, well, I know that the amount or the cost of this plus the cost of this needs to equal the cost of this. So if I take whatever this is and I add it to this, it needs to equal the total mixture, my 5 pounds here. So that means I'm going to take this value, I'm going to have 575K plus 4.5 and then 5 minus K. Those two things added together need to equal the total cost of the mixture. All right, so there they are. I got 5.75 and then I'm going to work through this problem. For the sake of time, I'm not going to do that. All right, but what you need to do is you distribute here and then you multiply. You end up solving for K. You should know how to do this. You end up finding that K is 3. So if there's 3 pounds of Kentucky bluegrass, well, it's 5 minus K to find the tall fescue, which means the tall fescue must be 2 pounds overall. So there are my total weights right there. Again, I'm not going to work through that problem just for sake of time. I need you to do that on your own. But the most important thing on these problems is going to be setting up this table using the rate times time equals distance. Now, I know that's kind of weird to wrap your mind around, but that's really the best way to set this up. So here's one for you to try. The answer will be up in 3, 2, well, before that. Remember, when you find a percent of something, you're doing 0.15, okay? And it's a percent. So there's my hint to you. The percent is the rate. So try to do this one on your own. Answer will be up in 3, 2, 1. All right, so here's what I got. Here's how I set up my table. I have the drink, I have the pure pineapple, and I have the mix. Take a look at that. I make the distance or the totals right here added together. Here's how the equation sets up. So it's this plus this equals this. And then you solve for P and you end up getting 5.6 ounces. So if you didn't get that, go back, check your work, check your table against my table. All right, let's look at a distance problem here. It says a freight train left Cincinnati for San Francisco. 6 hours later, a passenger train left Cincinnati for same destination, So this is going to be a rate times time equals distance. And this one is actually using rate and distance, which is really, really nice. So we have two kind of trains here. We have a freight train. We have a passenger train. This is not a mixture problem, so I do not need that third row. When it's just straight up distance, 2 rows is going to be fine. All right, so then I go in and fill some things in from this problem. Okay, first of all, the passenger train travels 10 hours. That's right here. You should have read this problem, but I'm running out of time on my video, so I got to move quickly. The passenger train traveled for 10 hours, but it says 6 hours later the passenger train left. So if this train left 6 hours after the freight train, that means the freight train had been traveling for 16 hours. Okay, let's see, passenger train was going 60 miles per hour, and then what I want to find was the speed of the freight train, which I'm going to call F for the freight train. Now, that's how my table sets up, so let me go over that again. The rate of the freight train is what I'm trying to find. The time was 16 hours. The way I found that was that the passenger train traveled for 10 hours, and the freight train left 6 hours before the passenger train. Okay, so that's got to be 16 hours total. The rate of the passenger train is given, and so I take these things and I find my distance. So the speed times time will be the distance of the freight train. And then here I get 60 times 10 is the distance of my passenger train. And all I want to do on this one's a little bit simpler to set up than the ones we were just looking at, is I want to know when the distances are the same because it caught up to it. When it caught up to it, the distances were the same. So I get an equation like this that's pretty straightforward that I'm trying to solve. So I'm not going to go through this pretty simple equation. You should get it. You end up finding out that the freight train was going 37.5 miles per hour. And that's by setting the distances equal to each other. All right, so here's one for you to try. It sets up similarly. I do want to point something out. It says a 555-mile trip. Okay, we're talking about a trip that has 2 legs to it. All right, so in this one, you're not finding out when the distances are equal to one another. You're finding out when the 2 distances, when added together, are 555 miles. All right, so there's my hint for this one. Go ahead and pause and try to do this, making a table. And the answer will be up in 3, 2, 1. All right, so here's what I got. I got my rate times time. I call them legs of a trip. And so I filled in the stuff from the problem into my table. Your table should look similar. And then it's going to be the distance of leg 1 plus the distance of leg 2 equals the total distance of the trip. Then you solve for the time, you get 2 hours, which is this leg. So if this leg is 2 hours and the total is 5 hours, then that must mean the other leg is 3 hours. So leg 1's 2 hours at 105 miles per hour. Leg 2 is 3 hours at 115 miles per hour. So go back and check your work if you didn't find this, see what you did wrong. The one thing I want to say before I close out this video is that these problems are difficult. So do not get frustrated with yourself. They all kind of have the same setup, but they're at the same time all a little bit different in the way that they're going to set up. So don't get frustrated. We're going to take our time on this. I'm going to work with you in class a lot on this. So just keep chopping away and do not give up on this. I will see you all in class.